Welcome to Pre-Calculus. Today we will investigate representing arithmetic sequences using both explicit and recursive equations. And then we'll use those equations to predict a term in the sequence. Let's start off by looking at two examples that involve writing an explicit equation to represent a given arithmetic sequence. Our first example is given here with the first four terms 5, 25, 45, and 65. Ultimately, we want to write an explicit equation to use to find the 21st term in that sequence. So when we are writing an explicit formula, there's two things that we need to find. I need to find what we call the common difference, and I also need to discover my first term. And then I'm going to plug those into a formula that I've got for the explicit formula. So let's find those two things first. The first thing we can find very easily. So I'm going to identify the first term in the sequence, and I'm going to call that a sub 1. And that's simply 5. So whatever your first term is, that's what you would identify as your a sub 1. To find the common difference, I'm going to take two terms and I'm going to subtract the first from the second. So here I've got the first two terms, 5 and 25. 25 minus 5 would give us the difference of 20. Now it is called a common difference, so I also want to check the other pairs of terms in the given sequence to see is it also a common difference of 20. So here I've got 45 minus 25, that's 20 also. And 65 minus 45 confirms that. So my common difference here is going to be 20. Notice that's positive, which indicates that the sequence is increasing. And I can see that with my first four terms from 5 to 25 to 45 to 65. Those terms are getting larger and larger as they go. All I need now is the template. So the template for an explicit formula for an arithmetic sequence would go as follows. It's going to be a sub n equals my first term a sub 1 plus the common difference times n minus 1. And again, this sub n indicates which term each number is in the sequence. All I need to do is substitute the two values that I found. So I found that a sub 1 is 5, and I found the common difference is 20. And then I want to place the rest of the pieces around those two initial term and common difference. And once I have those two substituted in, that is my explicit formula. One thing we can do, since this really is a linear function, is simplify this explicit formula to something that looks like slope-intercept form, y equals mx plus b. And we do that just by simplifying, by distributing, and combining like terms. So I do want to distribute the 20 through the n minus 1. So that would give me a sub n equals 5 plus 20n minus 20. And then I see I've got constant common terms, the 5 and the negative 20. If I add those together, that's going to be negative 15. So final version for this formula is going to be a sub n equals 20n minus 15. Now, once I have that formula, for me to calculate, in this case, the 21st term, I want to find a sub 21. All I have to do is take the number that would identify the term in the sequence and plug that value in for n. So if I want to find a sub 21, I'm going to take the explicit formula we just wrote, and for n, I'm going to substitute in 21. And then I just need to multiply. So 20 times 21, if I multiply that out, that should give me about 420. And then 420 minus 15, my 21st term in the sequence is going to be 405. So that was an example of an arithmetic sequence that was increasing. Let's take a look at an example for a sequence that's decreasing. So notice my task is the same. I do want to, again, write an explicit formula, and then I want to find, in this case, the 30th term in the sequence, a sub 30. So I'll just start again by finding, first of all, my first term, a sub 1 for this sequence is going to be 25. And then I want to find also the common difference. So I'm going to take pairs of terms that are right next to each other, and then I'm going to subtract the second minus the first. 23 minus 25 is negative 2. 21 minus 23, also negative 2. And that's confirmed with my last pair of terms, 19 minus 21, negative 2. So the difference in this case is negative 2, which indicates to me that the sequence is decreasing. I'm going to plug those in again into my explicit formula. A sub n equals a sub 1 plus the common difference times n minus 1. So I'll substitute in my two values here, 25 for the first term, negative 2 for the common difference. And just like we did on the first example, I want to simplify this to a slope-intercept, y equals mx plus b form. So I'm going to distribute the negative 2, so that'll give me a sub n is 25 minus 2n plus 2. And then combining my common terms, 25 and 2, I'll get the final version here, negative 2n plus 27. Notice that if the sequence is decreasing, what we would call our slope will be negative. Whereas if the sequence is increasing, the slope will be positive. Again, if I want to find the 30th term, I'm going to take that explicit formula I just wrote and plug in 30 for n. And then again, simplify. So this is going to be negative 60. Negative 2 times 30 is negative 60 plus 27. And then negative 60 plus 27 is going to be negative 33. Negative 33. So those first two examples, we were writing an explicit formula. Let's take a look at how we would write a recursive formula. So here we've got another increasing arithmetic sequence. It starts 6, 15, 24, 33. So I want to write, in this case, a recursive formula. So the main difference between an explicit formula and a recursive formula is recursive defines the sequence in terms of, well, each term in terms of the previous term that came before it. So let's give ourselves a template for the recursive formula. This is a recursive formula template. And again, this is specifically for an arithmetic sequence. And that template would look as follows. That's going to be a sub n equals the previous term, which we're going to call a sub n minus 1. And that's going to be plus the common difference. So note, with a recursive formula like this, really all we need to find is the common difference. So again, we'll take our pairs of terms, 15 minus the one before it, 6. That will give us a common difference of 9. If we subtract our subsequent pairs, 24 minus 15 is also 9. And then 33 minus 24 confirms that that common difference is 9. So I'm going to record that. D is going to equal 6. And for a recursive formula, what we need to include are the first term, and then substituting this D value, the common difference, into the template, that formula. So we'll say our first term, a sub 1, is 6. And then my formula is going to be a sub n equals the previous term, a sub n minus 1, plus the common difference of 9. I see that I wrote it incorrectly above. D should be 9. So I'll go ahead and box that. That's my recursive formula. So again, different from an explicit formula, it really depends on the previous term to calculate the next one. Now, when I face a task like finding the 30th term in the sequence, a sub 30, really I see an advantage to having an explicit formula versus a recursive formula. With a recursive formula, I really have to just write out my list and then find the 30th term, whereas with an explicit formula, I can plug in the number of the term in the sequence into the formula and calculate directly. Well, let's go ahead and find the 30th term using the recursive formula, since that's what we've got, that's what we just created. So essentially, I just need to extend this list. I've got 4 terms now. I need to get out to 30 terms. So I'm just going to keep adding 9. So that's going to give me 42 for my 5th term, 51 for the 6th term, 60 for the 7th term, 69 for the 8th term, 78. 1, 2, 3, 4, 5, 6, 7, 8, 9 is my 9th term, and my 10th term is going to be 87. We'll do these in rows of 10. I'm going to continue the sequence below, so that becomes then 96, 105, 114, 123, 132, 141, 150, 4, 5, 6, there's 7 of those in that row, 159, 168, and 177. So that's 20 terms. We'll keep going. We've got 10 more. That would give me 186, adding 9. 195, 204, 213, 222, 231, 240, 249, 2 more, 258, and our 30th term is going to be 267. A sub 30, 267. So just comparing my explicit and my recursive formulas, really there's an advantage to the explicit in this instance where I'm trying to come up with a number in the sequence just based on where it falls. Well, let's take a look at one last example that would involve a decreasing sequence and writing a recursive formula for that. So again, for a recursive formula, what I need again is the template. A sub n equals the previous term, a sub n minus 1, plus the common difference. And again, I want to say what a sub 1 is. You always put both things together for a recursive formula. So I see my a sub 1 is going to be 23. And that's my first term. And then my common difference, again, I'm going to take pairs of terms that are right next to each other, subtract the second minus the previous. So negative 7 minus 23, that's negative 30. Similarly, negative 37 minus negative 7's negative 30. That's like negative 37 plus 7. and negative 67 minus negative 37, again, negative 30. So that common difference is clearly negative 30. And there's my recursive formula. It's going to be a sub 1 is 23, and then a sub n is the previous term, a sub n minus 1 minus 30. Here I want to find a sub 40. So again, the recursive formula, I'm really locked into finding all the terms in the sequence up to the 40th term. So that's not something I'm really interested in doing. The last example, we listed out 30 terms. I don't want to list out 40 terms. So what I want to do is I'll just find an explicit formula and use it to find that a sub 40 directly. Again, the explicit one has this form. It's a sub n equals a sub 1 plus d times n minus 1. And we've found these two pieces already that we need. A sub 1 is 23, and the common difference is minus 30. Again, all I need to do now to get that in mx plus b form is distribute the slope here, the common difference. So that's going to give me a sub n is 23 minus 30n, negative 30 times negative 1 plus 30. And then combining my constants, a sub n is negative 30n plus 53. So now I want to use that to find a sub 40. A sub 40 equals negative 30 times 40 plus 53. So again, I'm using the explicit formula instead of the recursive one to find that 40th term. And we'll just calculate here. So 40 times 30 is going to give us 1,200 plus 53. So it's negative 1,200 plus 53. And that's going to give us negative 1,147. So definitely the 40th term would have required a lot of listing. Again, the advantage of an explicit formula, I can plug in the place, in this case the 40, directly into the equation and calculate. Thanks for joining for this investigation of writing or representing arithmetic sequences using explicit and recursive equations. See you soon.